In this part of the video, I'm going to talk about doing linear regression with a binary predictor instead of a continuous numeric predictor. And I'm going to walk through how to do it in R, just like I did with the continuous predictor. And I'm working with this part of the code file, regressiondemos.r. So here we're about to walk through it in R, but first I want to explain what the material variable actually is before we go about using it. The goal here is going to be to use the material variable, which is metal or plastic, to predict the price variable, which is a dollar amount that we're using as our response in our regression models. And from last week, you know that you can use a binary predictor in a regression model, no problem. Essentially, you code it as zeros and ones. And I want to show what R is going to do with material, which is stored as a factor, when we include it in our regression model. So let's think about a different example. Let's suppose that we have a data set like this one shown on the screen, where we have a participant number, they have an age, a binary indicator of whether they're a transfer student or not, and most importantly, a variable called major_string, which specifies their major. And all of these students majored either in psychology, English, or math, and psych is written abbreviated psych. So there's three unique values, but they're being stored as strings of characters here. Most of the time when we have a categorical variable like this, we don't want it to be treated as arbitrary strings. Instead, we want it to be treated as a set of categories. So we will instead tell R to store it as a factor. So here there's a copy of the variable that I'm calling major_factor, and let's suppose it also has these categories labeled psych, English, and math. But I've sort of shaded it in gray here to illustrate this is not actually how R stores the information about the categories in a factor. Instead, it's a little bit more complicated than that. So major_factor actually is a set of integer values, 1, 2, and 3. And also, attached to that set of integer values, there's some metadata about those integer values. And all of this is encapsulated in the factor data type. So major_factor has values like 3, 1, and 2, but in the background, connected to those values, there's a reference table about what the levels of the factor are, sort of like a key that says that 1 means English, 2 means math, and 3 means psych. This is what we would get by default if we converted major_string to a factor, because it alphabetizes the levels by default, but you can change what order they show up in, and that can matter for some types of analysis. So in this case, 1 is English, 2 is math, 3 is psych. So these are not actual numbers. 3 is not 3 times as much as 1. They're being stored as integers in order to make it easy to look them up in this table, but R understands, because it's a factor, that they're supposed to be categories. And there's another piece of metadata that's stored along with this factor variable type, which is a set of contrasts. Here, there are 2 contrasts because there are 3 categories in the variable. Those contrasts are a representation of what's going to happen to that factor if you include it in a statistical model. So here, contrast 1 is called math, and there's a table indicating that contrast 1 math is represented by zeros for English, ones for math, and zeros for psych. The row names here represent the actual categories of the factor, and the contrasts represent how those categories will be encoded for each of the variables that actually get included in a regression model when you plug this in as a predictor. So math will essentially be a vectors of zeros and ones corresponding to this factor variable, but with all the English students converted to 0, psych students converted to 0, and math students converted to 1. And that's not enough to fully cover the information in this factor, so we need a second contrast, which by default will be called psych, and we'll have zeros for English majors, zeros for math majors, and ones for psych majors. The reference category by default will be the first one in alphabetical order, but you can change that and I'll show you how. The result of this is that these 2 contrasts together will fully cover the information contained in this major factor, because students who have a 1 on contrast 1 are math majors, those who have a 1 on contrast 2 are psych majors, and those who don't have a 1 on either of those contrasts are the reference category, English majors. This is what those predictor vectors will look like in the background when they're being included in the regression model. You won't actually have to see a column called major factor math that has zeros for psych and English and ones for math majors. And you won't have to see a column called major factor psych that has 1s for psych majors and 0s for these other categories. But they will kind of implicitly exist because when you get your regression model output, you'll have slopes corresponding to these two predictor vectors. This is a useful way to include this factor in a regression model without having to manually calculate these 1s and 0s yourself. So here we are back in R, and let's go back to thinking about robots. We have this material variable, which is metal or plastic. There's 263 metal robots and 247 plastic robots. And its class is factor, which is nice to know because we want it to be a factor when we include it as a predictor in the regression model. We can use the contrasts function to view what the contrasts will be when we plug this factor into a regression model. And in this case, we only need one contrast because it's binary. That contrast will be called plastic, and it will have metal values coded as 0 and plastic values coded as 1, which is perfectly reasonable. Metal will be the reference category, and we will be comparing plastic to metal. So now I'm going to fit the model. Again, I'm going to store the result of the LM function in an object called mod_material. That's an arbitrary name I created just to keep track of the results of the LM function. Price is my response variable. The tilde separates it from the predictor. Material is the predictor, which is a binary factor, but could be any variable type that would be useful for predicting price. And they came from the robots data frame. I'm going to look at a summary of that model object. And we can see that there is a intercept of 107.50 and a slope of negative 9.98 for material plastic. The intercept represents the fitted value for the metal robots of price, and it corresponds precisely to the average price of the metal robots in this data set. Metal robots cost $108 on average. And material plastic represents the difference in price between metal robots and plastic robots. Negative 9.98 means that the plastic robots were, on average, $9.98 less expensive than the metal robots. The difference between the metal and plastic robots was statistically significant. We can use the confint function to get a confidence interval for the intercept and the slope. So this confidence interval represents a 95% confidence interval for the mean value of the metal robots. And this confidence interval represents a 95% confidence interval for the difference between the metal and plastic robots. We can view the means directly in order to see that this interpretation makes sense. The mean price for metal robots is 107.501, which is the intercept we saw here. And the mean value for the plastic robots is 97.52, which should be 9.98 less than 107.50. How did I get these two means using this code? tapply is a handy function. It can do a lot of things, but the easiest way to use it is to provide a vector as the first argument, a numeric vector that you want to do something to, usually numeric, and a categorical vector like a factor as the second argument. In this case, material has two categories, metal and plastic. And the third argument should be a function that you want to apply to this numeric vector for each category of this categorical vector, and then any additional arguments to pass to this function. So na.rm equals true is necessary in order to use the mean function in most of the cases where we'll want to use it, because usually we have missing values in our data set, and usually we just want to omit them from the calculation of mean. So what this will do is calculate the mean of price, removing missing values, for each of the materials, and then give it to you in a vector like this. If we use the plot function with price tilde material, like I said before, it will assume that we want price on the y-axis, and it will guess how we want to handle the x-axis based on the type of the variable material. So here is that plot, and it gives us a box plot by default, which is a pretty handy way to represent distributions of price for levels of a categorical variable. And although the means are not directly shown in this box plot, we can see that the distribution for the metal robots does seem to be elevated relative to the distribution for plastic robots, consistent with our idea that the metal robots are more expensive on average. Let's make a copy of the material variable that's stored as 1s and 0s ourselves in order to practice thinking about what R does when we include a factor in a regression model. I'm going to make a new variable called robots $plastic. Plastic is a vector stored in the robots data frame. And I'm assigning it the result of this asNumeric function call. The argument to asNumeric is testing whether material is equal to plastic. Robots $material is a vector. We've been working with it all along. Double equal sign tests for equality. And so this portion of the line of code will return a vector of trues and falses where the trues correspond to the plastic robots and the falses correspond to the metal robots. Converting that vector to numeric turns it into a vector of ones and zeros where the ones correspond to the plastic robots and the zeros correspond to the metal robots. And that is perfectly reasonable to include as an additional variable in the robots data frame so that we can use it in some analysis. Here's an illustration of that. This is the first 20 rows of the data set, just looking at material and plastic columns. And we can see that when the material was plastic, the plastic variable is 1, and when the material was metal, the plastic variable is 0. The square brackets allow me to retrieve a subset of a data frame. So I got this by just looking at the robots data frame, but with square brackets to specify which part of it I want to look at. And before the comma inside the square brackets, I specify which rows I want. The colon gives me a vector of integers ranging from 1 to 20. So I want all of the rows between 1 and 20 inclusive. After the comma allows me to specify which columns I want. And here I've used C to create a temporary vector that has two values, material and plastic, as strings. Those are the names of the two columns I want to keep. I could have provided the column numbers if I wanted to, just like I did with the rows, but in this case I found it easier to refer to those columns by name. And just to reassure ourselves that our conversion worked perfectly, I've created a two-dimensional table of the values of material and plastic, and we can see that all of the values that were metal got turned into 0, and all of the values that were plastic got turned into 1. So with this new variable, we can get a different kind of plot. I've called the plot function with price tilde plastic this time instead of material. And now plastic is a numeric variable, it's zeros and ones. So we will not get a box plot, we'll get a regular old scatter plot. And I can plot the regression line on it using AB line from the mod_material regression model. This works because the reference category was metal in mod_material, and we know that the plastic variable that we created matches the contrast that was used for the material variable when we included it in a regression model, where 0 is metal and 1 is plastic. So here are the values of price for the metal robots, plotted in this vertical column at 0, representing the metal robots. And here are the values of price for the plastic robots. And this line passes through the mean of those two clusters of values. And that's what it means to fit a linear regression model on a binary predictor. Here's the model summary again using the material predictor. And here's a model summary that uses price as the response variable and plastic as the predictor instead of material. Plastic is this new column of zeros and ones that we made. And you can plug the LM function directly into summary. You don't have to store its result and then plug the result into summary. In this case, I'm doing that because I'm not going to do anything else with this version of the model. I'm only showing it to illustrate that it's exactly the same regression model. The intercept is the same. The slope is the same. Everything about the model output is the same, because converting the material vector to a column of ones and zeros, where 0 represented metal and 1 represented plastic, is exactly what R did when we plugged the factor material into the right-hand side of the regression model anyway. So doing it manually was just to illustrate that that's what happened. You would never really need to do that manually. That is, you don't need to make your own indicator variables, variables of ones and zeros, also called dummy variables, in order to use factors in your regression models in R. But it's nice to know what's going on behind the scenes with your factors. And if you plan to use SPSS for statistical analysis, you will need to make your own indicator variables, like we did here, at least if you want to use the ordinary regression command. The regression command in SPSS does not handle categorical variables or even interactions for that matter in a sensible way on its own. But there is a workaround in SPSS. So if you try this a few times and you want to keep using SPSS and you get sick of manually preparing categorical variables in interaction terms, talk to me later about using the mixed command to avoid having to do that. Finally, I want to show the result of the t.test function. So here's that model summary again with mod_material, with material plastic as the indicator, as the contrast that's included in the model for the material factor. And here is the result of calling t.test on the formula price tilde material, which is the same formula we used for mod_material, with the same data frame and this argument specifying that we do want to assume that the variances are equal. This, as you should recall from last week, is equivalent to the regression model with this same model formula. The conventional student's t-test that assumes that variances are equal compares these two means by calculating the difference between these two means in the group metal and in the group plastic and dividing it by the standard error of that difference. And this regression model calculates a slope, which is the difference between these two means, and divides it by the standard error of that slope, which is the standard error of the difference between these two means. So the p-value is the same. Here it got rounded to 6 times 10 to the negative 7th instead of 5.996 times 10 to the negative 7th, but it's the same under the hood. The degrees of freedom is the same, the t-statistic is the same, and the underlying means are the same. This confidence interval is also the same as what we would get by calling conf_int on mod_material. You might notice that the t-statistic has the opposite sign. That's just because this model is testing how much lower plastic is than metal, and this one is testing how much higher metal is than plastic, but those are conceptually the same thing. Later in the semester, we will return to the idea of a t-test that does not make the assumption of equal variances. But for now, the types of regression models that we're talking about are equivalent to this type of t-test, and you don't really need to think of this t-test as being a different thing. If you understand regression, then you're good.